it does matter what direction you look in this sense. Because so far I've only treated this as a two-dimensional problem. Let's turn right back on and talk about what the third dimension would be. Because we're going to deal with three dimensions here in a minute for other things. I still turn on the wrong light. In this strain problem, this direction always stretches in the finite strain. So the long axis of this, or this part of the strain ellipse is going to stretch, and this side's always going to shorten. If you think about that circle. No matter what you do, this will always shorten, and this will stretch relative to the original objects. If you think now, start thinking in three dimensions instead of a circle, think about a sphere that has the same thing happen to it in this sense. So that when the material shears, this is the plane we're looking at right here. What is the length of line elements when I look down on that relative to those other two? Because this, in other words, when I look parallel to this, or I look parallel to this, what are there changes in line length? It's not a trick question. Oh, it's kind of. It's a little counterintuitive, because you've got to start thinking three dimensions. But look at this object. We were looking at everything we've been thinking about in this. Here's this thing, just like I had a sketch up on that. With asymmetry, this is top right shear. And so this deflection is related to the finite strain. Things are stretching in this direction, and they're shortening in this direction. What happens to a line that's lying in this direction? Or take a card deck. When you take the card deck, what happens to the lines on the top of the card deck?
It's longer?
I take a piece of paper, and I have this edge of this paper, and I do that. What happens to that line? Absolutely nothing. Right? Does that help? Because it's still a piece of paper, right? Now that's a theoretical experiment, but the idea is the same. That when you take this material and move like that, there's no changes in length in this dimension. That's a special state, actually, that we'll talk about in a second called plane strain. But what it means in this particular context is that if you look in this direction at a thing like this, you're going to completely the wrong idea of what's there. Because you're going to be just looking at things moving away from you or moving towards you. If you make some other arbitrary cut, God knows what you're going to see, because you're going to have some other funny orientation. What it does mean, and this will partly lead us into the next part of this discussion, let's think about lengths then. I said this one's always stretching, and this one's always shortening. If this dimension is not changing, then it's going to have a length somewhere between the length of that line and the length of that line. So that's an intermediate length. So there's a shape effect. That's a three dimensions. And I'll come back to that in a moment about object shapes. But what that really means is that in the third dimension, if you look down on that surface rather than sideways with it, in this surface, materials are also moving towards the stretching line. There's still a strain ellipse on this surface. So any surface in here has a strain ellipse if you cut it through it. But if you look down on that particular surface, there's still material stretching. What that produces in a rock is a lineation we'll talk about later. But the point is, what you really do in practical terms is look for those elements in the rock, and you find the right section, which is this section, which is the so-called movement plane. It'd be the same as in a fault, as if you're looking on a fault. It would be like looking on the plane perpendicular or parallel to the plane that contains the motion vector, but that's perpendicular to the slip line. The best example of that is a strike slip fault, a perfect strike slip fault. You're standing on what would be called the movement plane. The horizontal surface of the Earth would be the movement plane because everything is moving like this relative to you. And you always, that's the plane that's relevant to the shear sense that would be recognized within the material. Okay? Now again, I'm going to beat this in your head later when we talk more about rocks, but I wanted to introduce it here because of this sort of illustration of a practical application that's really important in this particular context. And what it tends to do is there's an illustration of this, of how if you look at objects that are looking on this particular surface, there would be no rational reason for any sort of rotational characteristic. It's acting like it's pure shear in that section, whereas on this section, or the movement plane section, you've got all this rotation going on. And so there are objects and things like that that get caught up in the flow that show the effects of that rotation. They're basically asymmetries at small scale that are mimicking this effect of the obliquity between the accumulation of finite strain and the shear within the material. There's a gazillion of these. I didn't do that. I guess I can go back. We'll come back to this later. There are got a whole bunch of different things that are used that are so-called shear sense indicators that simply exploit that relationship. That's the rotational characteristic, but you always have to think about them in the context of movement within that plane in the third dimension of how they move. Does that make any sense to anybody? Let's do a couple of quick applications of shear zone theory to show this a slightly different way, different scales that shows the effect of some of the things that can result, even counterintuitive, that are produced by the effects of shear versus just squashing something. And one of my favorites is the example of famous class of structures in the Alps called the alpine naps. The alpine naps are just giant overturned forms. They look something like that, right? So there's an upper part and then they lower, there's a huge overturned there's even a scale here, right? So there's like 15, 20 kilometers of a very large fold. When people first saw those, it was rather confusing, as you might guess, of how you could have such a large-scale feature. All of these rocks, in this particular case, are ductily deformed. They're all metamorphic rocks. But what you see on a large scale, and this is just the authors of this paper projected into the air structures that were a long trend from this. So at higher structural levels, or higher parts of the crust, there are regular run-of-the-mill thrust faults, such that you take older rocks and put them over the top and make just big stacked thrust sheets, and we'll talk about that later. But these things, if you take that analogy, if you're just going down and down, the material starts to flow, the analogy that's made is this is nothing more than a large ductile shear zone. And that's why you can carry the tail of this system, because think about how that works in the context. If I start with sediments or layered sedimentary rocks, they're not going to be sediments by the time they get here, right? And I make a shear zone that cuts across those. What's going to happen in that context? That's like taking shear zone model we just talked about. The beds, the sedimentary beds, find themselves in this orientation as this thing starts to move as a thrust fault, right? But they're not going to start as a fault. What happens to them? They're going to first fold. Oops, let me stick with the right color thing. As that progresses, they'll do just like that diagram we just said. They're going to start to fold because they're going to shorten. But then as strain progresses, they'll go. They rotate through the flow and they get pulled out in the flow and they become they get rotated backwards into a giant overturned limb, or they're just streaked out as the material rolls back on itself. And the effect is nothing more than a classic illustration of a shear zone. What's weird about it, of course, is that you see them here and you don't necessarily think about the fact that that's the way you see the fact that they roll over, you can understand that relationship, but you don't understand until you understand the context of a shear zone. They not only roll over, they also get stretched and pulled out like taffy on the bottom limb of that particular system. And it's simply the flow equivalent of a thrust flow. That was the simple characterization of that. So that's a simple application, if you will, of a shear zone model. Here's one of my own. I'll turn the lights back out for this one because you can't see it without it. This is one that I puzzled over because I couldn't figure out how this could be. So let me try to explain it. There's a bunch of stuff here you don't need to worry about at the moment. But they're shown in here are these little red streaks right here, which are dikes, igneous dikes, that although they're straight, they are deformed. When you look at them, you can tell they flowed. In this same area, we know that superimposed on top of this, there's a very strong effect of a right lateral shear sense, essentially a strike slip shear system. So these rocks were deforming. There's a longer history, but basically they're deforming a right lateral shear system in flow. These rocks are 600 degrees C at the time. Now, if you think about, maybe I should turn the light on for this one too. If you have material that's flowing, or that is affected by we're doing everything top to the right now, right? Makes it easier. I said a shortening axis is here, and the extension axis is here. So if there's a pluton, or an igneous rock, that's going to come into a rock that's under this condition, where are you likely to have an igneous rock come in? Notice where these are. They're in here, right? Would they really want to come in there? That would be the last place they'd want to go. Instead, they'd probably, theoretically you could show this, and that's the way it virtually always is they should be like this. Because this is the opening direction. So they're going to want to preferentially inject along the least stresses. That's what they do in hydrofracts, right? Mm-hmm. Actually, what they do in exploit in hydrofracking. So how come these dikes are oriented the wrong way? Is it just I'm wrong about their time period? Well, it turned out, in this particular case, that we were actually able to measure the amount of strain that was present within these dikes. And I remember what it was. Elliptices of like 5 to 1 or something, which equates to X amount of simple shear, right? If they're shearing in this sense, what happens to line elements that start here? They rotate. So these objects, even though they're nice little straight dikes, they were caught up in the flow, and they rotated in the flow by about 60 to 70 degrees because of the distributed shear. And their orientation now does not reflect their original orientation. So that if you were to look at them, as their orientation and not know that, you would think this was the shortening direction. This stuff's here, so it should have been going the opposite direction. But instead, the objects have rotated. Tricky problem. But it's an illustration. It's just another illustration of the importance of the distinction of shear versus other things and the way objects rotate. Yes, sir?
So what's going on with the one that's 91 APA33? It's in the middle. It's.
Which one? Oh, this one?
Dotted.
Oh, that's a different generation.
Oh, okay.
That's older. Yeah, it's much older actually, and that's part of the different part of the story. You're correct though. That one is oriented this direction. If you look at, it's actually a different color on the map, so whatever. It's orange instead of pink. But you can't see that from there. Any other questions?
Well, I mean, if that's older, wouldn't it also be deformed in that direction? Or?
Yeah, but it's even more deformed because there's another history of this rock that I glossed over here.
Okay.
There's another part of the story that's irrelevant for this discussion. Okay, well, actually, I forgot to show here. I even show some strains here by the shapes of some of the objects here.
So the